So our next speaker is Rintaro Eto from Waseda University. Okay, nice.
Thanks. Do you see everything all right?
Yeah, yes.
Okay.
And the topic for his talk is about quantum damping of the chiral magnons in Altermagnetism. And with that, I'll hand it over to Rintaro.
Okay, thanks. Thank you for introduction, and thanks for organizers for giving me a chance to talk about our recent research results. I'm Rintaro Eto from Waseda University in Japan. Today, I'm going to tell you about the quantum spin dynamics in altermagnets. This work has been done with these collaborators, especially with the supervision of Alexander Mook in University of Münster. Okay, let's first introduce the altermagnetism. As many of you know, altermagnetism is a recently reclassified class of non-relativistic collinear magnetism. On the basis of these very great seminal works, this pairs of work gives the trichotomy classification of non-relativistic collinear magnetism, including conventional ferromagnetism, antiferromagnetism, and altermagnetism. Altermagnetism exhibits the compensated magnetic texture like antiferromagnets, but even parity spin splitting, which breaks a time reversal symmetry, which is similar to ferromagnetism. So we can regard this altermagnetism as a hybrid of conventional ferromagnetism and antiferromagnetism. And this work focuses on the quasi-particle excitation in altermagnets, especially magnons in altermagnets. Actually, there is already several very nice works working on magnons in altermagnets. This work studies the magnons in altermagnetic ruthenium dioxide using first principles. And they found that the magnons in altermagnets are less affected by the Landau damping, where the magnon decay into particle hole continuum. So we can generally say that the magnons in altermagnets are much stable compared to those in conventional antiferromagnets. And also the subsequent works using a random phase approximation for Hubbard model study revealed the sizable angular dependence of such Landau damping in metallic altermagnets. On the other hand, in insulating altermagnets, some very nice works using quantum simulations like DMRG or some tensor network techniques show that the magnon excitation spectrum in insulating altermagnets cannot well described by the usual linear spin wave theory, meaning that a significant quantum fluctuation effect take place. But of course, such non-perturbative quantum simulation cannot tell us why such quantum effect take place or quantum effect contributes to excitation spectrum. So to understand such microscopic details of magnons in altermagnets, including fluctuation effects, we need to build up the kind of bottom-up theory. And this is a focus of this work. And this slide shows the kind of overview of this work. Actually, the conventional dichotomy of magnon stability in non-relativistic collinear magnets splits into these ferromagnetic case and antiferromagnetic case. The important thing is, except for this kind of very weird dispersion duration in antiferromagnets, the magnons in these conventional spin textures are in general stable. On the other hand, what we found here is in altermagnets, the spin split upper branch magnons can always decay into these three decay products, meaning that upper branch magnon is always unstable. So including all these three cases, we call this trichotomy of magnon stability in non-relativistic collinear magnets. And in the following, let's focus on the altermagnet, magnons in altermagnets. And to study the magnon excitation in altermagnets, let me start with this very simple D-wave altermagnetic checkerboard model. Now we have Nair vector, Nair magnetic order on the square lattice. So the nearest neighbor spin-spin interaction is J1 is antiferromagnetic. And we have two different, two inequivalent second nearest neighbor exchange interactions, J2 plus delta and J2 minus delta. This difference is associated with this arrangement of non-magnetic atoms. And this delta directly corresponds to the altermagnetic spin splitting in this model. So the Hamiltonian is given by this kind of formula. And to study the spin excitation, we expand each spin operator using Holstein-Primakov transformation like this, and taking all the terms up to the second order, which means the bilinear term, we get this kind of diagonalized form. And the dispersion relation epsilon k up or epsilon k down certainly shows this kind of D-wave spin split chiral magnons. And our focus here goes on the quantum physics in this model. So to study such quantum effects, we need to expand this square root and take the higher order process into account. And then we can systematically perform the perturbation expansion, and we can sort all the terms in terms of the Magnon numbers like this. This H0 corresponds to the classical energy because this is merely constant, and H2 corresponds to the linear spin wave theory. So the fluctuation effects comes from a 3 Magnon term, 4 Magnon term, or much higher order terms. But now we consider non-relativistic collinear system. So we have macroscopic U1 symmetry around the Nair vector. So this Magnon number conserving non-conserving H3 term cancels. So the leading quantum fluctuation contribution comes from these 4 Magnon terms. And actually this can be classified into 3 types of scattering process, including the Magnon number conserving 2 in 2 out process. And others are Magnon number non-conserving 1 in 3 out or 0 in 4 out process. And during all the scattering processes, some of the physical quantities are conserved, like total energy, total crystal momenta, and total spins. But this Magnon number is generally not conserved. And this non-conserved nature of Magnon number directly corresponds to the quantumness of this system. Okay, then we systematically perform the many-body perturbation theory and list all diagrammatic scattering process contributions. As a result, we get this all these 8 different types of scattering process in total. But physically important scattering process is only this 3 Magnon forward bubble scattering process. So in the following, let's focus only on this. And actually, this 3 Magnon scattering process certainly satisfy the aforementioned conservation laws. For example, if the inward and outward state has the crystal momentum k and spin up, the intermediate 3 states are 2 spin up states and 1 spin down states with total momentum conservation. And of course, total energy is also conserved. Actually, all these conservation laws are encoded into this spin resolved 3 Magnon density of states. And this color map shows this density of states. We can clearly see that the upper branch magnons are completely inside of this 3 Magnon continuum, while the lower branch magnons are just at the edges or lower bounds of this continuum, meaning that only upper branch magnons can decay into 3 particle states. Okay, then let's see the numerical result of a nonlinear spin wave theory. The upper panel shows the dispersion relation. The lines show the linear spin wave results, and markers shows the non-linear spin wave theory results, including quantum fluctuation contributions. As increasing the altermagnetic splitting delta, we see the altermagnetic spin splitting gets larger and larger. And at 1.0, we see very large spin splitting. And the interesting thing is, compared to the harmonic theory, linear spin wave theory, the quantum fluctuation reduces the spin splitting. Okay. And the lower panel shows the Magnon damping. And as increasing the splitting delta, we see the Magnon decay becomes larger and larger again. And at the largest splitting case, we see that only the upper branch Magnons have a significant decay, but lower branch Magnons cannot decay into these three particle states, meaning that only upper branch Magnons are unstable, but lower branch Magnons are stable. Okay. And we also compare our nonlinear spin wave perturbation results, this with non-perturbative density matrix renormalization group simulations performed by our collaborator Matthias. And the MRG shows that at the brilliance on edges, actually this pi over 2 point corresponds to M point, we see very sizable damping effect. We cannot see the clear spectral weights here. This kind of sizable damping is well reproduced by our nonlinear spin wave theory with offshore treatments, meaning that all the frequency dependence of the self-energy is properly taken into account. So we can generally say that at the brilliance on edges, the Magnon decay physics is most pronounced. Okay. We also study the long wavelength scaling of Magnon decay, assuming this kind of very simple dispersion relation, which is only valid in the long wavelength limit. And for D-wave altermagnets, we generally found that along the spin split directions, the decay of upper branch Magnon scales as delta to 2, k to 5. On the other hand, along the nodal line of Magnons, the decay scales as k to 7 with some threshold behavior with respect to delta. Okay. And finally, we propose that the organic altermagnets, like this kind of this material, is a promising candidate of the predicted sizable Magnon decay, maybe using neutral scattering or some experimental techniques, because it hosts the spin 1/2, so the quantum fluctuation contributes very much. Okay. Let's summarize. Our very simple take-home message is spin split upper branch Magnons in D-wave altermagnets are generally unstable. Thank you for your attention.
Any questions? Okay. If not, I have a quick question. As an experimentalist, what would you suggest us to? How would you suggest us to do experiments or specific material to study to look for this effects?
Actually, maybe the most important thing is maybe the Magnon decay physics is measurable realistically only in D-wave altermagnets. Maybe in G or I wave or higher order altermagnets, maybe the spin split effect is not so significant. So maybe it's difficult to observe such a significant decay. And of course, it is important to choose the magnetic materials which has shorter spin length. In this sense, this material was spin 1/2. So I think it's very promising.
Thank you. And also Nuno, please go ahead.
Thank you very much, Rintaro, for your very nice talk. Actually, I think you answered in the end. to my question. I was going to ask why organic altermagnets? How did that idea came up? Is it because of quantum properties or just because of the plane, like you were talking about?
Okay. Yeah, so okay, yeah, the first thing is the organic, in general, organic materials tend to have shorter spins. And the second is the organic materials is composed of relatively light atoms, not the heavy atoms. So which means that spin orbit interaction do not contribute so much. So in this sense, that it is the good platform to study the non-relativistic physics. But this is my idea.
So there's a lot of materials used for molecular spintronics that are also based on organic.
I think so. Yes, I believe so.
Yeah. So it will be a nice platform to also get something experimental, just as Juni was discussing, I guess.
Yes.
Yeah, thank you.
Thank you very much.
Okay. If no more questions, let's thank the speaker again.
Thank you very much.
Yeah.